Welcome to lecture number 10. We're going to talk about partial derivatives. So let me just remind you what a one variable derivative looks like. This is Calc 1. So Leibniz notation, derivative of f is this limit, f of x plus h minus f of x over h. Now with a two variable function, we can choose where h goes. So for f of xy, we can put the x with the h with the x or the h with the y. And we call these two derivatives partial derivatives. So the partial with respect to x, the h is with the x, and the partial with respect to y, the h is with the y. But otherwise, they look virtually identical to the one derivative. Just a comment on notation, we also use f subscript x and f subscript y to reference these partial derivatives. Notice that these d's here are script d's, so this d is different from the d in the derivative of one variable. So if the graph is smooth, then the partials have a nice geometric meaning. Let me draw a picture to illustrate this. So say we have a function of two variables that looks like this. It's this curved surface. The partial with respect to x is going to be the slope in the x direction. So if we have a point here, its slope in the x direction, so it looks like that, is going to be described by the partial. Draw this little triangle. Rise over run is going to be that slope. And the partial with respect to y is going to be the slope in the y direction. So that's nice. It's very similar to derivatives of one variable, where if we have a curve, the derivative is the slope at a particular point on that curve. All right, let's do an example. So let's look at this function x squared times y and compute the partials at the point 1, 1, and then interpret these two partials geometrically. Okay, so we'll do the partial with respect to x first. So this is the limit as h goes to 0 of replacing every x with x plus h. So x plus h squared times y minus x squared times y all over h. So this is the function evaluated at x plus h, comma y, and then the function evaluated at x, y. And this is just going back to the definition up here. All right, and then what we do is we expand this expression, and then we combine like terms. So this will be x squared plus 2xh plus h squared all times y minus x squared y. And the x squared y and the x squared y are going to cancel, and we'll be left with 2xhy plus h squared y all over h. The h's cancel. This happens a lot in calculus 1. Same pattern emerging here. So there's an h in every term in the top, so that'll go away. So we'll have 2xy plus hy. And then this expression, as h goes to 0, becomes 2xy. So that's the partial with respect to x. Now let's do the partial with respect to y. Very similar. But instead of x being replaced by x plus h, we're going to have y being replaced by y plus h. And then we'll do the limit. So we'll get x squared y plus x squared h minus x squared y all over h. These cancel, and we're left with x squared h over h, which just becomes x squared. So we have the two partials. The partial with respect to x is 2xy. The partial with respect to y is x squared. Now we can evaluate these at the point 1, 1. The notation here is a little clunky, but it's what we have. So to evaluate this partial at 1, 1, we do this vertical line and then the point. So, and we put 1, 1 in for x and y, so that's 2. And then the partial with respect to y, that's going to be 1 squared, which is 1. So let's interpret these partial derivatives as slopes in the respective directions. So this partial derivative with respect to x, that's a slope of 2 in the x direction. So the claim is that slope is around 2 over 1. And then the partial with respect to y, that's the slope in this direction, the y direction, and that looks like slope 1. And this is the y direction, and this is the x direction.